Let's take a look now at section 1.7 and talk about linear, compound, and absolute value inequalities. In previous sections, we've seen several kinds of equations. An equation is a way of setting two expressions and comparing them to each other by saying this expression is the same as this other expression. However, an inequality is a different way of comparing two expressions. The inequalities, we're going to look at four different inequalities, although they're not exactly different. Some of them are related to each other. We're going to have is greater than and is less than. We'll talk about the other two in just a moment. Is greater than is a comparison of position along a number line. Whenever you have a number line, you have positive numbers to the right of 0, and you have negative numbers to the left of 0. That's a standard convention. That's the way we usually write a number line. When the number line is written this way, whenever we say something is greater than, we mean it's to the right of another number. So greater than or less than is a relative statement. For example, I can say 2 is greater than 1 because on the number line, 2 is to the right of 1. Of course, that symbol isn't always a symbol between 2 and 1. It's relative to whichever one we're referring to. Here, if we say 2 is greater than 1, that's the same as saying 1 is less than 2, right? Is less than. Because here, if 2 is on the right, well, it's greater. Well, then that means 1 is on the left, which means it's lesser. It's less than, right? Any number that's to the right is greater than any number that's on the left, right? So, for example, if I have the number 2 is greater than negative 3, right? Because of course 2 is to the right of negative 3, and negative 1 is less than 0, because again, negative 1 is to the left of 0. Okay? Now, we can compare individual numbers, and here, just by comparing their positions on the number line, we can say, okay, that's a true statement or it's a false statement, just like we can with an equation. Once we introduce a variable, though, we end up with a different interpretation. Whenever I have an equation, something like x equals to 5. Well, here, let me use x equals to 3 because I want something that's actually on my number line. So let's say x equals to 3. Whenever I say that, that means that there is one and only one number on the entire number line that satisfies this equation. And that would be this number right here. Whenever we say x equals to a number, then there's one and only one solution to that equation, and that is that one number. However, an inequality gives us a lot of solutions. If I say x is greater than 3, well, what I'm asking for is the numbers that are to the right of 3. But there's a lot of numbers to the right of 3. There's 4 and 5 and 6 and 7 and 50 and 100 and a million and a billion. They go on forever. In fact, we have a symbol for that. This number line never ends in either direction, right? Any number line will go on forever in either direction. So we have a symbol for that concept. This is read as infinity. Infinity is not a number. I can't say infinity is like a number like the number 5 or the number 2. I can't say that infinity is going to be added to infinity. I can't say infinity is going to be divided by 4. Infinity is not a number in the traditional sense. The way we're going to use infinity is as a symbol that tells us we're going to go toward the right without ever stopping. If I wanted to go from 3 up to 5, I would say from 3 to 5. If I wanted to go from 3 to 100, I would say from 3 to 100. But if I want to start from 3 and go forever to the right, I'm going to say from 3 to infinity. That doesn't mean we're ever going to reach infinity, because infinity is not a number that you can reach. Rather, we're saying you're going to go forever in that direction. Here, if we go forever in this direction, we call that infinity. Well, you could go forever in this direction. Yeah, but we don't want to use the same symbol. That could get confusing. So we'll put a negative in front. What this tells us is it goes forever in the negative direction. In other words, to the left. Some people actually write plus infinity right here, and that tells you it goes forever to the right versus forever to the left. Other people don't bother putting the plus here, and they'll just write infinity. Either one's okay. But this one we'll write as a negative infinity. So here, when we say we want all the numbers that are greater than 3, that means we want everything from 3 to the right forever. On the other hand, if I were to say I want x is less than 3, that would mean I want all the numbers from 3 to the left, going to negative infinity. Notice that that's not just a single solution. With an equation, you have a single number that makes that true. With an inequality, there's lots of numbers that make that true. The numbers that are less than 3 are 2 and 1, and -2 and -5 and -1,000,000, and so forth and so on. Whenever we have an inequality, we're going to have not just a single number, but a range of numbers. We're going to have numbers from one starting point to an ending point, or sometimes from a starting point on forever. So to signify that, we're going to write our solutions in what's called interval notation. The reason we use interval notation is because you can't actually list your solutions. If I said, I want all the numbers that are greater than 3, you'll never finish. You'll never be able to write a list of all the numbers that are greater than 3 because they keep going. You would never finish. So instead of trying to write a list, which will never finish, we have a different way of writing this. This is called interval notation. And interval notation is a way of writing out the numbers in an interval, starting from some place and ending at another place, or in some cases starting from a number and going on forever. Okay? The way we write this is, interval notation is kind of like drawing the number line without actually drawing the line. What I mean by that is, if I want all the numbers that are greater than 3, well, I would start at 3. Okay, so let me write that first. And then I would go forever to the right, going toward the infinity, going toward this end. So I'm going to write 3, comma, infinity. Because on the number line, the 3 is on the left and the infinity is on the right, I'm going to write that in that order, from 3 to infinity, from left to right. And then I'm going to put these in parentheses, like that. This signifies I want all the numbers from 3 to infinity. Notice, I don't actually want the number 3. 3 is not a solution to this. Why not? Well, because 3 is not greater than itself. 3 is not greater than 3. 3 is 3. So here, this does not include the number 3, just everything to the right of it. On the other hand, this one here, if I said x is less than 3, well, then I would want all of this stuff in red. Notice, all of this stuff goes all the way over here to negative infinity on the left, 3 on the right. So when I write that, I'm going to write that in order, negative infinity on the left and 3 on the right. Just like that. Now, you'll notice that in both of these cases, I don't include the number on the end. I don't include the number 3. Well, what if I need to? What if I said I want all the numbers that are greater than 3, but I also want to include the number 3? Well, that brings us to the other symbols, which are very closely related to the ones we already have. This one is read as is greater than. This one is almost exactly the same, but that extra line, this is read as is greater than or equal. And all this does is it includes the number on the end of the interval. So, for example, here, if I want to say x is greater than or equal to 3, I still want everything from 3 to infinity, right? Greater than 3. But the extra little line here, the extra equal to part, tells me that the number 3 itself, I also want to include that. I don't want to exclude it like I did before. Before I said, okay, 3 is not greater than 3, so it should be included. Now I actually do want to include it. So the way we write the interval notation, we're going to write the same thing, from 3 to infinity. But to signify that we want to include that number as part of our interval, we're going to use a square bracket. Likewise, if I want x is less than or equal to 3, it's the same as this, except now I want to include that number on the end. So it would be from negative infinity up to positive 3. And the only difference between this one and this one is that the 3 would be included as part of my set. It's part of the numbers that I want as my solutions. Whenever you include the endpoints, the endpoint of the interval, whenever you include the number 3 here or here, this is called an inclusive inequality for obvious reasons. You're including something, so we call it inclusive. These are called inclusive inequalities. Over here, you're excluding the endpoints. You're excluding the number 3, so it doesn't take any imagination. to realize these are called exclusive inequalities. They're exclusive because you're excluding something. Whenever you include a number, you're going to use a square bracket. And when you exclude, the parenthesis shows you that you go up to that number, but you don't include it. You exclude it. Okay. Over here, this one is less than or equal. Okay. Now, the interpretation of an inequality is different than in the interpretation of an equation. Notice here, if I say x equals a number, the interpretation is I have that one solution, and that's it. The number 3 is the one and only number in the whole universe that makes that true. Inequalities, there's lots of numbers which make inequalities true. All the numbers on this side make this inequality true. All the numbers on this side make this inequality true. So the interpretation, the meaning of the answer is different. Fortunately, the methods that we use to solve are very much the same. You're going to notice that most of the techniques that we see here, in fact, all except one, are going to look exactly the same as what we would do with an equation. Right? So let's start off with a quick visual. Let's say I have a number line. Let's just pretend that's a number line right there. Right? Okay. If I have a number line, there are numbers everywhere along this line. And here, let's just go ahead and do the typical thing where positive numbers are to the right and negative numbers are to the left. Okay, now, let's say I were to add 1 to every number on this number line. Well, if the number 0 is right here, well, then the number 0 would move 1 to the right. Okay, 0 plus 1 is 1. The number 1 would move 1 to the right. 1 plus 1 is 2. Okay? In fact, if I add 1 to every number on the number line, all that happens is that every number moves a little to the right. Okay, so really, you can think of it as the entire number line just shifts over. But notice that your inequalities have no reason to change. Everything that was greater before, everything that was on the right, is still on the right. Everything that was lesser, everything that's on the left, is still on the left. The fact that things slid over doesn't change that. Everything that was greater is still over here. Everything that was lesser is still over here. Well, okay, but what if instead of adding, what if I subtracted? Well, kind of the same thing. If I subtract 1 from every number on the number line, that means the entire number line just shifts over 1 step to the left. But again, everything that was greater before is still greater. All of this stuff is still over here. And everything that was lesser is still over here. Okay? Well, what about multiplication? What if I were to take the numbers on the number line and double them? Well, that's not really going to change the position of anything. Because, okay, yeah, it's true. My numbers will change. But notice that, well, if I have the number 1 and I, let's say, double it, that becomes the number 2. If I have the number 2 and I double it, that becomes the number 4. So really what's happening is this number line is getting longer. It's getting stretched out. But so what? The stuff that was bigger is still to the right, and the stuff that was lesser is still to the left. And if I were to cut everything in half on a number line, and I were to squeeze all the numbers closer together, it would shrink my number line down. But so what? Everything that was on the right, yeah, it's closer together, but it's still on the right, which means anything that was greater before is still greater, and anything that was lesser before is still lesser. So if I add or subtract or multiply or divide, my inequalities aren't really affected. Anything that was less than before is still less than. Anything that was greater than before is still greater than. Well, okay, but there is one exception. And that's what happens if you multiply or divide by a negative number. Because if you have a number line, let's say this is the number 5, right here. And let's say over here is the number -5. If I multiply everything times a -1, what's 5 times -1? Well, that's -5 now. So this goes from being a positive to being a negative. What happens if I take -5 times -1? Well, now that's a positive. So if I multiply everything by a negative, the numbers that were positive are now negative, and the numbers that are negative are now positive. Notice everything flips around. What that means is whatever used to be greater, remember this was on the right before, is now lesser. And everything that was lesser, remember this was on the left before, has now come to this side. It's greater than. So whenever we are simplifying to solve an inequality, you're going to notice that just about everything looks like what it looks like when you solve an equation. The one difference will be, now make a note of this, note if you multiply or divide an equation by a negative number, and it doesn't matter what negative number that is, as long as it's negative. It doesn't have to be -1, by a negative number, that should not be an equation. It should be an inequality. Then the inequality reverses. You can see that very simply with just a regular number. Let's say I start off with 2 is greater than 1. Let's say I add something to both sides of this equation. Let's say I add the number 4. Okay, well, 2 plus 4 is 6, and 1 plus 4 is 5. Well, yeah, but that's still greater than. All right? So if I add something to both sides of this equation, the inequality stays the same. Well, what if I subtract? Let's say I subtract 1 from both sides of the equation, or inequality. Well, 2 minus 1 is 1, and 1 minus 1 is 0. Well, yeah, but 1 is still greater than 0. So adding or subtracting doesn't change anything. All right? If I add 4 to both sides of my equation, or if I subtract 1 from both sides of my inequality, everything stays the same. If I multiply everything by the number 3, okay, well, 2 times 3 is 6, and 1 times 3 is 3. Well, that's still the same inequality. 6 is greater than 3. And if I cut everything in half, half of 2 is 1, and half of 1 is 1/2, and that's still 1 is greater than 1/2. So if I add or subtract or multiply or divide by any positive number, my inequalities stay the same. But notice what happens if I change this inequality by multiplying by a negative number. Let's say -2. Well, -2 times -2 times 2 is -4. -2 times 1 is -2. And now this inequality is reversed. Because notice on the number line, -4 is to the left of -2. -4 is to the left of -2, which means -4 is less than -2. So here, notice that your inequality stays the same, except for when you multiply or divide by a negative. If you multiply or divide an inequality by a negative number, and that's any negative number, the inequality will reverse. So let's take a look at some examples of how we can solve linear inequalities. Note that we're going to be writing our answers in interval notation, mostly because, well, we can't actually write them out the way we write solutions to equations. For an equation, you can write a list. Oh, my solutions are 2, 5, and -3. For an inequality, well, you have too many solutions to ever write down as a list. So we're going to use our interval notation. All right? So for our first example, let's go ahead and try, let's see here. Let's say we have -4 x plus 12 is greater than, let's say 60. All right. So to solve the inequality, we're going to pretty much do what we usually do, and that's we're going to isolate the variable, just like when you're solving an equation. The only difference is that in the process of solving the equation, if we ever multiply or divide by a negative number, that will affect the direction of our inequality. Otherwise, things work pretty much the same as they do with equations. So here, if I'm trying to isolate my x, let me get rid of that 12. All right, so that goes away. And I'm left with -4x is greater than, let's see, 60 minus 12, that's going to be 48. Notice, I subtracted a number. Subtracting a number does not change my inequality. That greater than is still greater than. Okay, let's continue isolating here. Let me get rid of that -4, and I'm going to do that by dividing both sides by a -4. Notice that I've now multiplied, or I guess I should say divided, negative 4 on both sides. So by dividing both sides by a negative, that's going to reverse my inequality. So now instead of greater than, this is now less than. Negative 4 divides negative 4. That gives me just 1x, which is what I want. I want 1x. 48 divided by negative 4 is negative 12. And there we go. To write our answer in interval notation, it is helpful to imagine what the number line looks like. Now, of course, you guys can't see inside my head, so you can't see what I'm imagining, so I'm going to draw it out. Okay, here's a number line. I'm not going to write out all the details. I'm going to write out just the most basic form of our number line. Here's a line. Negative infinity goes to the left, positive infinity to the right. Here, I'm going to start counting from negative 12. Okay, so from negative 12, I want all the x's that are less than negative 12. Or in other words, I want all the x's that are to the left of negative 12. Right? Incidentally, that's what these symbols are. They're arrows. You imagine that's an arrow pointing to the left. Same thing over here. That's an arrow pointing to the right. But in any event, here x is less than negative 12. That means I want all the stuff to the left of negative 12. So I want all this stuff. All right, well, that's all the stuff between negative infinity up to negative 12. So my interval notation is from negative infinity on the left to negative 12 on the right. Always go left to right. Here, this is an exclusive inequality. We do not want to include the negative 12, right? This was not greater than or equal to. It was just greater than. This is not less than or equal to. It's just less than. So here we're going to use round parentheses to show that we're going to want everything between these numbers, but not that number itself. For our next example, note that sometimes your inequalities are just a little bit more involved. There's some more stuff going on. That doesn't really change how it works. It just means you have to simplify before you start solving. So let's consider an inequality that looks like negative 14 is less than or equal to 3 times x minus 7 in parentheses plus 7. Just like that. That looks a little more complicated, but really it's just because you have some terms that you can distribute and other terms that you can combine. So this isn't really significantly different. We just have to simplify first. All right, so let's distribute our 3. So negative 14 is less than or equal to 3x minus 21, 3 times x and 3 times negative 7, plus our 7 there. We can combine those like terms. Negative 21 plus 7 is negative 14. Negative 14 is less than or equal to 3x minus 14. And now we can proceed to isolate our variable. I want to get that x by itself. So let's add 14 to both sides. That makes that go away. And that's going to give me 0 is less than or equal to 3x. Just like that. And finally, if I want to isolate my variable, I want to get that x by itself, let me divide both sides by 3. Notice that in this case, I never multiplied or divided by a negative. Right? Here I added, and here I divided by a positive. So my inequality never changed. It stayed less than all the way through. So here I get 0 is less than or equal to x. Now, sometimes people have a hard time with that. People get used to x is greater than something or x is less than something. It looks a little weird when it's the other way around, right? 0 is less than x or 0 is greater than x. But remember, you can always reverse an inequality just like you can with a number. Right? We said previously, if I have 2 is greater than 1, that's the same as saying 1 is less than 2. Right? If I want to switch these positions, well, then I'd have to switch the inequality. If 2 is greater than 1, then 1 is less than 2. So here, if 0 is less than or equal to x, that's the same as saying x is greater than or equal to 0. Right? If 0 is less than x, that means x is greater than 0 or equal to. So now we can go ahead and write our result. Here, again, we're going to imagine a number line. And in my case, I'm going to draw it. So infinity to the right, negative infinity to the left, and here's 0 in the middle. And what I want is I want all the numbers that are greater than or equal to 0. Okay, so equal to 0, that means 0 is going to be part of my answers. Greater than means everything to the right of 0. So all of this stuff. So my solution is everything from 0 on the left out to infinity on the right. And remember, the order does matter, from left to right every time. Here we want to include that 0 as part of our solutions. And we're going to do that by using a bracket. This is what tells you that this is an inclusive inequality. And whenever you have an inclusive inequality, you include the boundary point. Infinity is still not included. You're still not going to put a bracket here. Why not? Well, because if you put a bracket somewhere, that means that that number is part of your answers. Infinity is not a number. It's not something you're ever going to reach. So here, infinity is not included because it can't be included. Infinity can't be a solution because it's not really a number. All this says is you're starting from 0 and you're going to keep going to the right forever. So that's the way we would write our interval notation. Right. So go ahead and give this a try. Go ahead and try x plus 3 all over 4 minus 3x plus 1 all over 6 is greater than negative 1 over 12. Okay. Now, again, this one looks a little more complicated than the very first one we did, but it's not really any different. This is still an inequality. The only difference here is that you have some things you can simplify. One thing you could do is you could actually divide these. You can write this as 1/4 x plus 3/4. You could write that as 1/2 x plus 1/6. The other thing you can do, though, is, well, you have a set of denominators, which means you can find a common denominator and that will help you clear them. So either way, you can either write them as fractions, separating them out, or you can clear your fractions. Either way, simplify first, solve, and then write your answer in interval notation. Go ahead and pause the video and work through the problem. And once you have a solution, go ahead and unpause the video and we'll go through it together. All right, so since I'd rather not work with fractions if I can avoid it, I think the better thing to do here is I'm going to clear the fractions. I note that I have a common denominator here of 12. Now, I have other common denominators. I could use 24. I could use 120. But 12 is the smallest one, which means I'll have the easiest time using it. Smaller numbers are going to be easier to use than larger numbers. So the smallest common denominator here is 12. So what I'm going to do is I'm going to multiply everything by the number 12. Just like that. Well, since I'm dividing by 12, notice that means some of my terms are going to reduce now. All right. 12 over 4, well, that's just the number 3. All right, 12 divided by 4 is 3. This term, I can reduce to lowest terms by saying, okay, 12 over 6, well, that's just the number 2. And here, 12 over 12, well, that's just the number 1. So now I can rewrite this inequality as 3 times x plus 3 minus 2 times 3x plus 1 is greater than negative 1. Notice here I multiplied by a positive 12, so my inequality hasn't changed. It only changes when I multiply by a negative. Okay, so that's a little bit better. I don't have any more fractions. Oh, but I can simplify some more. Let me go ahead and distribute here. That's going to give me 3x. That's going to give me plus 9. Negative 2 times 3x is negative 6x. And negative 2 times 1 is negative 2. Like that. And then I can combine my like terms. 3x minus 6x is negative 3x. 9 minus 2 is going to be 7. Just like that. All right, so now let me isolate my variable. I have that extra plus 7 there, which means I can subtract 7 from both sides. Adding or subtracting doesn't change your inequality. So that's going to be minus 3x is greater than negative 8. And finally, I'm going to go ahead and divide both sides by a negative 3. And notice that I'm dividing by a negative, so now my inequality will change. This is now a positive x. This greater than is now a less than. And here a negative divided by a negative is a positive. Positive 8 over 3. And there we go. So that is equivalent to all of this. But now, from here, we can write our solution. Imagine your number line. In my case, you can't see what I'm imagining, so I'm going to draw it. From negative infinity to infinity, I have 8/3 right here. And I want x to be less than 8/3. Not equal to 8/3, but less than. So from 8/3, I want all the stuff to the left. So that's going to be everything from negative infinity up to 8/3. We never include the infinities. Well, you cannot have a square bracket around that, so automatically that's going to have a round parenthesis. Here, 8/3, that's an exclusive inequality. It's going to exclude this number on the end. It's not going to include it. It's going to exclude it. So we use that round parenthesis to signify that. And this is our set of solutions. Now, sometimes, whenever we have an inequality, the inequality that we need is a little more complicated that can be stated by a single inequality. Meaning we have more conditions, we have more things that we need to say, and one inequality is just not enough to say it. So that's when we use what are called compound inequalities. Whenever we compound an inequality, there's going to be two ways we can compound them, meaning two ways we can combine them. There's going to be and there's going to be or. Depending on the course, you might also call these conjunctions and disjunctions, but here we're just going to stick with these. When we say and or, what we mean is how we're sticking the two inequalities together. If we have two different inequalities, and means we want both of them to be true. I need this to be true and this to be true. Or means it's okay as long as one of them is true. Either the first one's true or the second one is true. So that's going to give us two different ways of combining the results of an inequality. Conjunctions and disjunctions, or as we're going to call them, ands versus ors. Okay? So let's go ahead and take a look at an example of the first variety. We're going to talk about and. Okay? So let's see here. Let's say I have the inequality 3x minus 5 is greater than or equal to 2. Separately, we're going to have the inequality 2x plus 9 is less than or equal to 1. And these are two separate inequalities. But we're going to stick them together using this word right here. We're going to say and. That would be different if we stuck it together using this word. But we'll talk about this one separately in a little while. All right, so whenever we have a conjunction, we're going to treat these as two separate problems until the very end. So let's solve both of them. Let's not worry about this one when we solve that one. Let's not worry about that one when we solve this one. Let's keep them separate for right now. All right, well, solving these doesn't take too much effort. A little addition gets rid of that 5. And then we can divide to get rid of that 3. So that gets us x is greater than or equal to 7/3. Okay. Now separately, we're going to go ahead and solve this one. Let's say we have we're going to subtract 9 from here, and that's going to be 2x is less than or equal to negative 8. Let me go ahead and start off with these the other way around. Let me start off with this one being less than. Just to make the first one easier to draw out. All right, so let's start with the problems this way. All right, so now we're solving for x. We divide both sides by 2. And that's going to be x is greater than or equal to negative 4. Okay. So here we had just two separate inequalities, each of which we solve on their own. Okay. And in fact here, these have nothing to do with each other. These have two different sets of solutions. But now, when we say the word and, what we mean is, in order for this to be a satisfactory solution to both of them, we need to find where the solutions overlap. We mean that literally. Imagine you have a number line. And on your number line, you have negative infinity to the left and positive infinity to the right. Okay. So now, whenever we say x is greater than or equal to negative 4, that means that from negative 4, I'll put that negative 4 right here, I want everything that's greater than or equal to that. So from the negative 4, I want everything to the right. I want all of this stuff out to infinity. Okay, but now this one says I want x to be less than or equal to 7/3. In other words, I don't want to go past 7/3 to the right. I'm going to say from 7/3 on to negative infinity to the left. If x is less than 7/3, that means from 7/3, I want all the stuff that's to the left. When we say and, what we mean is we want this overlap. We want to find where this inequality is satisfied. Well, that's all the stuff in red. But we also want to find where all this stuff is satisfied. Well, that's all the stuff in blue. Okay, now where are they both satisfied? Well, that's wherever you have some red and some blue. Oh, it's where they overlap. So whenever we say we have a conjunction, whenever we say we want an inequality and another inequality, what we mean is we want to find where they overlap. Here, the interval notation is I want all the stuff starting from negative 4 on the left. I don't want to go out to infinity. I'm only going to go up to 7/3. So from negative 4 to 7/3, here I was including the negative 7/3. That's less than or equal to. So let me go ahead and put a bracket there to show that it's including that number. And here I'm going to include the negative 4 as well. So just like that. So this is a compound inequality. It's solved by solving two separate inequalities and then finding how they interact with each other. Try one. Same kind. We're going to do an example of and. All right, so give this a try. Go ahead and solve the compound inequality. Remember, you're going to solve each one on its own, and then in the end, you're going to see where the overlap is. So go ahead and try 5x plus 3 is greater than or equal to 18, and 5 minus 2x is greater than negative 7. Okay? So solve the compound inequality, and in the end, make sure your answer is written in interval notation. Go ahead and pause the video, give this a try, and whenever you're done, you can unpause the video and we'll go through it together. All right, let's take a look. We're going to solve each on its own. So right here, let's go ahead and subtract 3 from both sides. That goes away. And that'll give us 5x is greater than or equal to 15. And then divide both sides by 5. That'll give us x is greater than or equal to 3. Now, here, we can subtract 5 from both sides. All right, well, that's going to give us negative 2x is greater than negative 12. And now, let me divide both sides by a negative 2 here and here to isolate our x. Now, notice we divided by a negative, so that's going to change the inequality from greater than to less than. Negative 12 divided by negative 2 is positive 6. Okay? So on our number line, we want everything that's greater than or equal to 3. So here's 3, and greater means to the right. But we also want everything that's less than 6. Okay, so here's 6. Don't include the 6. All right, that's less than, not less than or equal to. So everything to the left of 6. And since this is and, what we want to do is we want to find where they overlap. Well, here where they overlap is all the stuff from 3 to 6. Include the 3, but not the 6. So from 3 to 6, include the 3, but not the 6. And there is our solution to our compound inequality. Let's take a look at the other kind of compound inequality that we have, and that's an or statement, also called a disjunction. Okay. So consider, for example, 2x plus 5 is greater than or equal to 17. And now instead of saying and, we're going to say or. And let's try 3 minus 2x is greater than 5. Just like that. All right. So we're going to, just like before, we're going to solve each one on its own. Let's go ahead and isolate our variable. Subtract 5 from both sides. So that'll get us 2x is greater than or equal to 12. And then we can go ahead and divide both sides by 2 to get x is greater than or equal to 6. Over here, we're going to go ahead and subtract 3 from both sides. So that'll get me minus 2x is greater than positive 2. 5 minus 3 is positive 2. And then we can divide both sides by a negative 2. Note, since you're dividing by a negative, that will change your inequality. So now instead of greater than, we're going to have less than. So x is less than a negative 1. Okay? With an and statement, you're looking for where they overlap. With an or statement, you're looking for any number that solves at least one part of the compound inequality. X is greater than or equal to 6. All right, well, here's 6, and greater than 6 means to the right. It's greater than or equal to, so we're going to go ahead and include the 6 as part of our inequality. So from 6 to the right. Over here, we want x to be less than negative 1. Okay, so here's negative 1. And less than negative 1, we don't include the negative 1. I'll use around parentheses to show it's not included. And then to the left is all the stuff going this way. Notice these don't overlap, but that doesn't matter here. And is asking for where do they overlap. Or is saying, where is there a solution to any of these inequalities? In other words, anywhere I've shaded is part of my solution. So here, this is all the stuff from negative infinity to negative 1. And I'm using round parentheses because that was exclusive. And then I also want all the stuff from 6 to infinity. And that one's inclusive because that's greater than or equal to. Whenever you have a solution like this, which is made up of multiple pieces that are disconnected, we join them together using what's called the union symbol. Union just means there are separate pieces that we need to put together to make one full answer. And this is our solution to our compound inequality. All of the solutions that work either for this or for this. They don't have to work for both. As long as it works for one or the other, that's these right here. So go ahead and give this a try. Go ahead and solve the compound inequality. 5 minus 3x is less than 11. Or 2x plus 12 is less than or equal to 2. All right. Go ahead and pause the video, solve the compound inequality, write the answer in interval notation, and once you're done, you can unpause the video and we'll go through it together. All right, so we can solve each one on their own. Let's solve for x here. Subtracting 5 from both sides. That'll give me minus 3x is less than 6. And then I can divide both sides by a negative 3. And that'll give me x. Since I've divided by a negative, that's going to reverse my inequality. So less than is now greater than a negative 2. I can solve this one by subtracting 12 from both sides. So that's going to give me 2x is less than or equal to 10. Oh, sorry, that should be negative 10. And then I can go ahead and divide both sides by 2. That's a positive, so my inequality doesn't change there. So that's going to be x is less than or equal to negative 5. And again, we're looking for the values which solve either component of my compound inequality. So this is going to go from negative infinity to infinity on my number line. Here, I want to limit it to anything which is anything which is greater than negative 2. Okay, so here's negative 2. Greater than means to the right, just like that. And then over here, I want everything that's less than or equal to a negative 5. So this does include the negative 5. And less than means to the left. A disjunction, a compound inequality with the word or joining the two inequalities, is asking for the union of anything that solves either inequality. So here we want everything from negative infinity up to negative 5, and that does include the negative 5, as you see here. That's less than or equal to. And then separately, we want all the stuff from negative 2 to infinity, greater than negative 2, and this one does not include that negative 2. And since you have two different pieces to one answer, we join them together as the union of those pieces. The union means those two separate intervals come together to give you one answer. And that's your result. The last kind of inequality that we're going to look at is the absolute value inequality. The absolute value inequality is exactly what it sounds like. It's an inequality that involves an absolute value. The nice thing about absolute value inequalities is that they are essentially compound inequalities with one extra step. So consider the simplest of all possible absolute value inequalities, the ones that only have a single variable and a single number. Let's say I have the absolute value of x, okay? Not x plus 5 or 2x plus 9 or anything like that, just x. And let's compare an equation versus an inequality with a greater than symbol and an inequality with a less than symbol. If I say the absolute value of x is less than 3, we saw in a previous section what that meant. That meant there's two numbers which make that true. The two numbers that are 3 steps away from 0, namely the number 3 and the number negative 3. Okay? Now, absolute value of x is greater than 3. Remember what absolute value means. It means the distance away from the number 0. That's why here I can say what number is 3 steps away from the number 0. Oh, well, there's two of them, positive 3 and negative 3. The same thing holds if I say, instead of how many steps can I take away from 0, I can say, well, what if I want to go past that? I can say I want the absolute value not to be 3, but to be greater than 3. If you still think about it in terms of the number of steps, what this is saying is, what are the numbers that are more than 3 steps away from 0? Oh, well, there's a bunch of those. There's a bunch of numbers that are more than 3 steps away from 0. You could go to the left and say negative 4, negative 5, negative 6, negative 7, forever, going out to negative infinity. Or you can go to the right. Once you get past 3, you could say 4 or 5 or 6 or 10 or 1,000 or 1,000,000 or 1,000,000,000, out to infinity. Every one of those numbers, along with every one of those numbers, has an absolute value that's greater than 3. But notice, that's what a disjunction looks like. That's what an or compound inequality looks like. It's two separate pieces that join together as one answer. So this is basically just a compound inequality. Likewise here, if I said I want absolute value of x to be less than 3, well then we're asking for all the numbers that are less than 3 steps away from 0. Okay, well then that's all of these numbers that are close to 0 until I get to the number 3. And likewise, all of these numbers that are close to the number 0 until I get to negative 3. All of these are less than 3 steps away from 0. 1 step or 2 steps or 2.5 steps away from 0. Oh, but that's just all the stuff in between two endpoints. Notice, that's what a conjunction looks like. That's what a compound inequality with the word and looks like. So whenever you see a absolute value inequality, you can think of these as being either an and statement or an or statement. And once you think about it that way, it becomes much simpler. Basically, we're just doing what we just finished doing with that one extra step of, okay, which one am I thinking about? Am I thinking of and or am I thinking of or? So for example, I'm going to go ahead and solve the absolute value inequality. I'm going to solve. Oh, let's try this one. 2 times the absolute value of 6 minus x minus 3 is less than 7. Just like that. All right, so first of all, I want to isolate my absolute values. Sometimes this less than or greater than will be misleading. It looks like I should have greater than, and really it should be less than, because when I isolate my inequality, I'm going to end up changing my inequalities. Remember, you can change inequalities if there's ever a multiplication or division by a negative number. So we don't want to assume anything just yet. Let's start by isolating the absolute values, and once you have absolute value is greater than, well, then you know it's this one. Or once you have absolute value is less than, then you'll know it's this one. All right? So let's not make any assumptions at the beginning. Let's just isolate before we do anything else. So here that'll be 2 times the absolute value of 6 minus x is less than 10. And then I can divide both sides by 2. And that'll be absolute value of 6 minus x is less than 5. Okay. So now I have this absolute value is less than a number. Oh, that's this case. Absolute value is less than a number. So that can be written as an AND statement. Say, okay, well, how do I do that? How do I write that as an AND statement? We're going to separate this into 2 separate inequalities. After all, that's what an AND statement looks like. It's 2 separate inequalities. And you solve each one on their own and then stick them together at the end. Okay, so what's the correct way to split this? We're going to do it this way. We're going to say 6 minus x. Notice, and we want everything to be less than this positive number. At the same time, we want everything to be greater than this negative number. So we're going to want this stuff here to be less than the positive version of this. But at the same time, we also want this stuff in the absolute value to be greater than the negative version of this. So if you have absolute value is less than 5, you want the stuff inside the absolute value to be less than 5 and greater than negative 5. So this is an AND statement. And again, you know that's the case because you have absolute value is less than a number. Absolute value is less than a number. Right? So now we can solve each of these inequalities on their own and then stick them together by finding where they overlap. Let me go ahead and get rid of that 6. That's going to give me minus x is greater than minus 11. And then let me multiply both sides by a negative 1 to get that negative x to become a positive. Since I'm multiplying by a negative, that's going to change my inequality. And now I have x is less than 11. On this other side, I can do the same thing. I can say subtract 6. That's going to give me a minus x is less than 5 minus 6 is negative 1. Now let me multiply both sides by a negative 1. Like that. And that's going to give me a positive x is greater than a positive 1. So now, on my number line, from negative infinity to infinity, I want all the stuff that's less than 11. Okay, so here's 11, and I want everything less than that. But I also want x to be greater than 1. So from 1, I want to go to the right. And what I'm looking for is where do they overlap? Oh, well, the overlap is all this stuff in here. Notice I don't want to include the 1, so that's going to be a round parenthesis. Notice I don't want to include the 11, so that's also a round parenthesis. So I want all the stuff between 1 and 11, but not including the endpoints, not including the 1 or the 11. So in the end, my solution is everything from 1 up to 11, but not including either one. And there we go. So whenever you have a absolute value inequality, what you're going to do is you're going to first isolate your absolute value, get that absolute value by itself. And once you have that, depending on what the symbol is here, you're either going to treat it as an AND statement in the case of less than a number, or an OR statement in the case of greater than a number. Once you know which one to treat it as, you're going to split it, solve the compound inequality. So let's take a look at an example of the other case where we have an OR statement. We're going to solve the following. So let's try 5 times the absolute value of x plus 1 minus 9 is greater than or equal to negative 4. Just like that. All right, so once again, first of all, before we make any decisions, we want to go ahead and isolate our absolute values. So let's add 9 to both sides. That gets us 5 times the absolute value of x plus 1 is greater than or equal to 5. And then if I divide both sides by 5, that'll give me absolute value of x plus 1 is greater than or equal to 1. Okay, so we have a greater than or equal to, which up here, greater than, splits up as an OR statement. All right, so here we go. Whenever we split this up as an OR statement, it's going to split into two separate inequalities that are being joined as a compound inequality using the word OR. All right, so what they're going to split up as is, notice your OR inequality. We want everything that's greater than the positive version of the number or less than the negative. Greater than the positive or less than the negative. So here we want our x plus 1 to be greater than the positive version of this number, in other words, greater than 1, or we want it to be less than the negative version of that number, in other words, less than negative 1. So now we can solve each of these on their own. Both of these are very short. We just have one step. We're going to subtract 1 from both sides, and we're done. So here this will give me just an x is less than negative 2. And here this will give me just an x is greater than or equal to 0. That should be greater than or equal to, right? Less than or equal to. So now, an OR statement doesn't look for where they overlap. It simply looks for where do I have a solution to anything? Where do I have even one solution? Or sorry, where do I have a solution to even one of the inequalities? So here's my number line from negative infinity to infinity. Here I want all the stuff from negative 2 to the left, that's less than or equal to negative 2. And here I want all the stuff that's greater than or equal to 0. So here's 0 and greater, so to the right. An OR statement is asking for a disjunction. It's asking for not an overlap, but where is there a solution to even one of these? So here you notice this is a solution to this, and all of this stuff is a solution to this. So by putting them together, we have our solution set is everything from negative infinity to negative 2. Notice this does include the negative 2. That's less than or equal to. Likewise, we have everything from 0 to infinity, and that does include the 0. Since these are two separate intervals, two separate pieces to one answer, we join them together using the union symbol, and that's our result. So go ahead and give this a try. You don't know ahead of time which one this is. It's either going to be an AND or an OR. It's going to be an absolute value inequality. So go through, first isolate the absolute value. Then once it's isolated, use that to decide which kind of compound inequality it is, and then go ahead and solve. It's got to be one of these two. So go ahead and give that a try. Go ahead and solve the absolute value inequality. 15 is less than the absolute value of negative 2x minus 3. And then outside the absolute values, you can have a plus 6, just like that. So give that a try. Go ahead and pause the video. And when you have a solution, go ahead and unpause and we'll finish it off together. All right, so let's take a look here. First of all, we want to isolate our inequalities. So let's go ahead and get this 6 out of the way. If I subtract 6 from both sides, I get 9 is less than absolute value of negative 2x minus 3 like that. Now notice that over here, I usually have the absolute value on the right side. On the left side. Whereas here I have it on the right side. There's nothing wrong with that. And if you can keep it straight in your head, it doesn't really matter which one it is. However, if you want it to look just like one of these, to make sure you make no mistake, you can always reverse those. Right? If 9 is less than the absolute value, that means the absolute value is greater than 9. If 9 is lesser, that means this one is greater. So if you want to write it the other way around, that's fine too. If 9 is lesser, then the absolute value is greater. So now it becomes completely obvious which of these it looks like. I have an absolute value is greater than a number. Oh, that's going to be an OR statement. Okay, so let's go ahead and write this as an OR statement. The way that works is, again, we want the stuff in the absolute values, the minus 2x minus 3. We want it to be less than the negative version of that number or greater than the positive version of that number. So now we can solve each of those on their own. Let's add a 3 to both sides of the inequality. Here, this is going to give me negative 2x. That's 0. That goes away. And negative 9 plus 3 is negative 6. And then over here, same thing. I can go ahead and divide both sides by negative 2. Notice that by dividing by a negative, that's going to reverse my inequality. And, well, that's just what it is. So that's going to be x. This is now greater than, and this is a negative 3. Over here, again, we're dividing by a negative. So that's going to be positive x. This will also reverse to be less than, and this will be negative 6. So now, you can imagine this, you can visualize this. You can't see inside my head, so I'm actually going to draw it. Here, x is greater than negative 3. That means from negative 3 to the right. X is less than negative 6. So from negative 6 to the left. Right? So we don't want to include either of those numbers. That's not greater than or equal to. It's not less than or equal to. So in the end, our solutions, everything from here to here, and also everything from here to here. This one or this one. So everything from negative infinity to negative 6, union with everything from 3 to infinity, negative 3 to infinity, forms our solution set. Just like that. Finally, we have a special case. Sometimes special cases means that they're more complicated, they're harder, or there's something that's exceptional to them. In this case, the special case is actually much simpler. There is one type of absolute value inequality that gives you an automatic answer, meaning there's no work to do, there's nothing else to say. Just because of the nature of absolute values, you automatically get a result. That's an equation, or rather an inequality, that compares an absolute value to a negative. At first, it doesn't look any different from any other problem we've done, but when you go through and actually start doing it, you see the difference. So let's say you have absolute value of 12 minus 5x. That's multiplied times 2 plus 6 is greater than or equal to 4. All right. So here, this doesn't look any different from the previous problems we've done. What we're going to do is we're going to start off by isolating the absolute value, because we would then try to see, okay, can we rewrite this as an AND statement or an OR statement? Okay, so far nothing different or exceptional has happened. Let's go ahead and isolate the absolute values. Let's subtract 6 from both sides. And now let's go ahead and divide both sides by 2 to get that absolute value completely by itself. Okay. So that's going to be absolute value of 12 minus 5x is greater than or equal to negative 1. All right. We can now stop. We're done. Because notice what this is saying. The absolute value of a number is greater than negative 1. Remember, absolute values are the number of steps away from 0. You can't have negative steps. You're either taking a step to the right or a step to the left, or 2 to the right or 2 to the left, but there are no negative steps. The number of steps you can take, the smallest number of steps you can take is 0. So here, the absolute value of a number, whatever that number might be, has to be 0 or greater. Okay, so here this is 0 or greater. In other words, it's a positive number. Here, what this question is really saying is, what positive numbers are greater than -1? Well, all of them. Every positive number. This is going to be some positive number. Well, it doesn't matter what positive number it is. Positive numbers are always greater than or equal to -1. So here, without having to go through any more work, without having to go through and writing it as a conjunction or a disjunction, without having to write it as a compound inequality, we can just say, oh, what absolute value is greater than -1? All of them. Doesn't matter what x is. This is always going to be greater than -1. So here, every real number is a solution. Since you're supposed to be writing the answer in interval notation, the way to write every real number is to say, well, I want the entire number line. Okay, well, that's just going from -infinity to infinity. There's never a stop in between, just from -infinity to infinity. Okay, so just write that, from -infinity to infinity. So if you write it out as a sentence, you would say every real number is a solution. If you write it out in interval notation, which again your homework will ask you for, this would be the interval notation, from -infinity to infinity. And there we go, that's it. If the inequality is in the other direction, you get a different answer, but again, one that's automatic. Let's say I had absolute value of 4 minus 3x. Let's say plus 5. And let's have that be less than 2. All right, same thing. At first, it doesn't really look any different than any other inequality, but when you isolate the absolute value, that's when you notice a difference. If we subtract 5 from both sides, that goes away. And I'm left with the absolute value of 4 minus 3x is less than -3. And now I'm done. Because over here we were saying what positive number, after all, absolute values have to be positive or 0. What positive number is greater than -1? Well, all of them. They're all greater than -1, right? So every real number works. This one's saying something very different. This one's saying what positive number is less than a negative? Well, none of them, right? If this is a positive number, it can't be less than -3 because positive numbers are always on the right side of the number line, never to the left. So here, this can't ever happen. It doesn't matter what number goes in here. It will never be less than -3. Okay, so then this inequality has no solutions. Just like that. Right? How do you write that in interval notation? There's actually a couple of ways to write it in interval notation. One way to do it is to just write empty parentheses. So we can do it this way. Whenever we write empty parentheses, we use what are called braces. It's just a convention. It's a notational convention. Here we're saying, okay, there's a set of things with nothing inside. So this is one way of writing what's called the empty set. In other words, a set of things which has nothing inside. Here, every solution works. So we're writing out the entire number line from -infinity to +infinity. Here, nothing works. So we're saying, well, we have a blank number line, nothing in there. The other way to write this is you write a circle with a dash through it like that. And that's another symbol that means the empty set. This is not the number 0. It's not the letter O or anything like that. It's actually just a circle. It's a circle with a line through it. And both of these mean the empty set. This empty set is used a lot more with a lot more detail in other courses, but for us, all it's going to mean is if you're using one of these symbols, that means you have no solutions, and that's how you write it for interval notation. This is how you write no solutions for interval notation. Whenever you have an absolute value that's either greater than a negative or less than a negative, you can pretty much stop, right? That's going to give you an automatic answer. Absolute values are always greater than a negative, and they're never less than a negative. Right? So that's it for the section, and that's it for inequalities. If you have any questions, comments, or problems, please make a note of them, write them down. You can email me or talk to me during our next meeting, and I hope everyone has a nice day.